Indeed, less than 0.2. Epsilon is 0.2. We see it here. This and this, 0.2. That's epsilon. Very good. Perfect example. So in this case, we know that this is 0.1. Would you agree? And we know that this is 0.3. Would you agree? So delta will always be the minimum of 0.1 and 0.3. Which one is the smallest? 0.1. So the answer is 0.1. Here's why. If you remember, we talked about that. 0.1 will be this interval. I'm going to use a different color. And 0.3 will be this interval. And here is the potential problem. If I use the bigger of the two, I could potentially make a mistake, or not make a mistake, just pick x here. And as you see, the f of x, f of this x, is outside of that plus or minus epsilon. 1 plus epsilon, 1 minus epsilon. So that's why I can never use the larger. I always have to use the smaller, because the smaller guarantees any x I pick here, it will fall within epsilon distance away from 1. That's all we needed to do here. Yes, please. Next question.
Just on what continuity?
Yes, continuity. Yes, let's take a look.
So it's the values of a and b in this one?
Yes, so we have f of x. We have x squared minus 4 over x minus 2 for x less than 2. We have a x squared minus bx plus 3 for 2 and 3. And then 4x minus a plus b for x greater than or equal to 3. Very good. Perfect example. Let's work on it. Okay, so first of all, I see this expression, and I'll say to myself, I don't like it, because I know I can factor it. I have x plus 2x minus 2 divided by x minus 2, and I'll simplify. X is not 2. I don't have to state x not equal 2, because x is not 2 here. And the simplified form will be x plus 2. So that's the first thing. I simplify the function as much as I can, if I can. So then the function we look at is this. It's f of x equals x plus 2 for x less than 2. It's ax squared minus bx plus 3 for 2 between 2 and 3. And it's 4x minus a plus b for x greater than or equal to 3. I haven't started doing anything, right? I just simplified one branch of the function. Any questions? Any questions? Okay, so the first step that I have to present on the test or final exam, not in WebAssign of course, is this, that x plus 2, ax squared minus bx plus 3, and 4x minus a plus b are continuous. As what type of functions? Excellent. As polyfunctions. Excellent. Now, in step 2, I have to find or talk or discuss or study what? Continuity at exactly at x equals 2. In step 3, I will study continuity at so the next step is continuity at x equals 2, and the last step will be continuity at x equals 3. Very good. Excellent. So I know the definition of continuity at a point. Limit as x approaches 2 from the left, from which branch? Awesome. Equals limit as x approaches 2 from the right, from which branch? Two from the right. Careful. 2 from the right. Ax squared. Is that clear? Yes? Because 2 from the left is here and 2 from the right is here. There is no 2 from the right or left here, right? Okay. So equals f of 2. Good. So can anyone give us this?
Sorry, is it 4?
Of course. Can anyone give us this? Yes, 4a. Good. Awesome. Plus? Very good. And now which branch do I use? Top or middle for x equals 2? Middle, correct? I don't have to write it again. It's the same thing, right? 4a minus 2b plus c plus 3. So I'm going to write it, but there is no need. So then I'm going to call this equation A. What equation A? What do I mean by equation A? I'm going to move 3 to the other side. 4a minus 2b equals 1. This is equation A. Good. So now the next step, you already told me, number 3. And the last step is continuity at x equals 3. Awesome. So then that means limit as x approaches 3 from the left. Which branch?
The last
3 from the left.
one.
The middle one. Very good. Ax squared minus bx plus 3 equals limit as x approaches 3 from the right from, yes, very good, 4x minus a plus b must equal f of 3. Okay, so can anyone give us this?
9a minus
Yes, 9a, very good, minus,
3b
yes, plus 3, very good, equals,
12 minus a.
minus a plus b equals, where do I plug in 3? Very good, so I get the same thing, 12 minus a plus b. 12 minus a plus b. This is what I care about. And from here, I will get equation uppercase B. So I'll move terms around for equation B and put it in correct order. I'm adding A. I'm subtracting B. And I'm subtracting 3. This is equation B. So now I create a system with equation A and equation B. 4a minus 2b equals 1 and 10a minus 4b equals 9. Next step, please. What do I do with this? Yes, how? You want to substitute? Is it what you said?
Yeah.
Too difficult.
Elimination.
Yes. Let's say I want to eliminate b. What do I multiply the top by? Very good. Awesome. So negative 8a plus 4b equals negative 2. 10a minus 4b equals 9. So 2a equals 7. How much is a? Is this good? Yes, but not good enough. I have to go back to any of the two equations. It doesn't matter. Let's say I go back to part B, to equation B. 10 times 7/2 minus 4b equals 9. Of course, I'll simplify. So I get 35 minus 4b equals 9, or negative 4b equals 9 minus 35, which is negative 26. So therefore, b equals 13 over 2. This was a long problem. Now, this is good, but not good enough. I have to present the function that is guaranteed to be continuous everywhere. And like 5 pages before I had it, yep. So x plus 2 for x less than 2. 7/2 x squared minus 13/2 x plus 3. And 4x, and I have negative a plus b. So negative 7 plus 13 is 6. 6 divided by 2 is 3. Negative 7 and 13/2, yes, 6 over 2, so that's 3. Yes, this was a more complicated problem than the one we looked at in class. Why? Because it had 3 branches and it had 2 unknowns, lowercase a, lowercase b. Very good. Thank you for bringing that to class. Anything else? Is there anything else that we need to look at?
Number
Yes?
4 for the definition of the limit.
Okay, do we have it? Which one is 4?
This way.
Okay. Okay, so we have limit as x approaches 0, e to 2x minus 1 divided by x, they say it's 2. Illustrate the definition by finding the largest possible values of delta that correspond to epsilon equals 0.7 and 0.3. So we're going to do just one of them, okay?
Okay.
You want to do the second one?
Yes.
Okay, so let's do the second one. Good. Thank you very much. Okay, so we're asked to find delta for epsilon being 0.3. So we know that for every epsilon, in this case for epsilon equals 0.3, I will find the delta such that x minus 0 less than delta will imply e to 2x minus 1 over x minus 2 is less than 0.3. So first I'd like to check, and I can check because it's 0 over 0, right? They say that the limit is 2. I need to make sure that it's correct. And I have a technique that I will teach you, but I can't teach you it right now. So this is going to be e to 2x times 2, and the denominator, so 0. Yes, it is correct. So the limit is 2, and we will get to that. After chapter 2, right before we even finish chapter 2, I will teach you that technique. Okay, so the whole problem reduces to solving this inequality and getting something like this. If I solve this inequality and I get something like this, this will be my delta. So I'll start. I don't know how to solve this, a particular technique. We will have to use a calculator. There is no way we can do this by hand. But I will write negative 0.3 less than e to 2x minus 1, and I'll multiply this by x, minus 2x divided by x less than 0.3. And with a graphing calculator, I will try to solve this equation it's an inequality, but first I'll have to solve the equation. With the graphing calculator, I will solve this equation first, and then find out delta. So there is no other way. So on this side, if I put in the graphing calculator, and that's how we have to start. In the graphing calculator, I will put e to 2x minus 1 minus 2x divided by x minus 0.3 equals 0 to find the solution. And the same thing on the other side, e to 2x minus 1 minus 2x divided by x plus 0.3 equals 0. And I have to see what we get. So let's go to the graphing calculator, and let's put that in. So in y equals, let me go back to second and table set, because as I said, this computer has the deep freeze or whatever it's called. So they erase everything. So I'll go to y equals. No, I don't want that. I want this. Okay, and we have in parentheses for the top, e. Here it is e. E raised to 2x and minus 1. And then plus, no, also still minus 2x, and then minus 0.3x. I'm finding the least common denominator. And then everything divided by x, but there is no need. Once I multiply that, x cannot be 0 anyway. So obviously I no longer need parentheses. I'm going to delete them, only because I multiplied. I found the least common denominator. Well, let me not confuse you. I mean, I just put the whole thing. It doesn't matter, really. When I solve the equation, it doesn't matter if I have the denominator in there or not. But let's say. Okay. So then we go with second and calc. And we want to find the 0. And we see the 0 is between -1 and 0. So the left bound, I'm going to put -1. And the right bound, I'm just going to drag it or use the, it doesn't allow me to drag it. So no, I don't want it that far. That's fine. So it will give us, I don't want to guess. So x is, so the solution of this is x equals -0.25. What? How many decimal digits they want, or did they say any of that or not? Did they say? Did they say in the problem or not?
3.
3?
3 decimal places.
Okay, so then 259 is okay for this one. So then I will go back to y equals, and I will change, the only thing that changes is the plus here. So plus, and I go back to second and calc, and I want the 0. Okay, so again, I have to determine, just making sure that I have everything correct. Yes, plus 0.3x minus 1 minus 2x plus 0.3x. Yes, okay. And I go to second and calc. Again, -1. I want the 0. It's 2. So the left bound, -1. And the right bound, make sure you pass the x-intercept. And I don't want to guess. And we got, for the second one, -0.314. Okay, so what did we accomplish? What did we accomplish so far? We are basically saying that x in absolute value is less than 0.259 or x in absolute value is less than 0.314. So the question was asking us to find the largest possible delta, but we know we cannot choose the biggest one. So the largest is confusing a little bit. So the largest one cannot be bigger than the smallest. So delta has to be the smallest of the two, for the same reason that we saw right here. So if one is 0.259, it's this situation. If the other one is 0.314, it's this situation. And I have no choice but choose the smallest of the two. Very good questions. Anything else? Is there anything else? Okay, so then we go back to trying to finish up this chapter. We are deep into 2.6. We did not finish 2.6. We have a couple of things that I have to look at with you. We talked about horizontal asymptotes. We talked about vertical asymptotes, and we're going to choose a problem like this in which we're asked to find all asymptotes. That's one situation that I like to look at. And of course, a problem in which we are given all sorts of conditions and we are asked to come up with an example of a function. Any questions? And then we can continue. There is nothing else here. And then we can continue to and move on to the last two sections. The last two sections we will always combine together because they're referring to the same thing. Okay, so let's start with problem, let's say 44 on page 141. We have y equals 1 plus x to the fourth divided by x squared minus x to the fourth. The problem is asking us find the horizontal and vertical asymptotes of each curve. If you have a graphing device, check if you want. There is no need, but yes, we can do that too. So we know two things. First of all, this is what type of function? What type? It's a ratio of two polynomials. It cannot be a polynomial. A polynomial cannot have a fraction with x in the denominator. So what is it? Excellent. Rational. Thank you. It is a rational function. It is a ratio of two polynomials. I have to agree with that. Good. So a rational function can have both vertical and horizontal asymptotes. So for vertical, I have to make sure that the denominator is never 0, right? So vertical asymptotes come from denominator equals 0, right? Now, the horizontal asymptotes in this case, it's a rational. I shouldn't even put plural because it's only one. They come from limit at positive and negative infinity. As x approaches positive or negative infinity of f of x. So there are two different situations. There is a third one that I like to talk about right here. The third one is no vertical asymptote. Here's a situation with no vertical asymptote. This rational function, I claim it has no vertical asymptote. What would be the restriction for this? what is the x value that we cannot have here?
Cannot be 1.
It cannot be 1. And however, how come, I should say, if x cannot be 1, how come that this is not a vertical asymptote? That's what we know.
Because it'll make a hole instead.
It's a hole because the factor goes away. If the factor that creates 0 in the denominator goes away, this function is still undefined at 1, but the x equals 1 is a hole, not a VA, only because the factor went away. So the new function is just 1 over x squared plus 1. The original function is still undefined at 1. But 1, x equals 1 is not a vertical asymptote. So basically, we will encounter kind of 3 different situations for a function that we have to look at. Vertical asymptotes, potentially holes in the graph, and horizontal asymptotes. Okay, so let's start by looking at which one would you like to start with. I would prefer to start with vertical asymptotes, and then look at horizontal, and then we'll see if there is a hole in the graph. Ready? Okay. So for this function, I will arrange it in the correct order. I will factor negative x squared in the denominator and also arrange it in descending order. And I will continue factoring, and we know how to factor x squared minus 1. So this is negative x squared and x plus 1, x minus 1. Do you agree with this so far? So one more time, from here, I rearrange it into negative x squared plus x to the 4th plus x squared. I factor out negative x squared. If you need to check, negative x squared times x squared is that. Negative x squared times negative 1 is positive x squared. And we have 4 factors in the denominator. However, 2 are the same. These 2 are the same. So then, you will give me 3 restrictions. Right? You'll say x not equal. Excellent. X not equal. Okay. And x not equal. Very good. Any of these factors disappears with an identical factor from the top? Can I simplify x squared with an x squared or an x from the top? No. Can I simply, or it has to be x squared. Can I simplify x plus 1 with a factor of x plus 1 from the top? What about x minus 1? So then I know for sure that all these mean vertical asymptotes. You will see that this is not enough. I have to find the limits, left and right. I know the answer is correct. I know it's vertical asymptote, but I still have to find the limit as x approaches 0 from the left. Limit as x approaches 0 from the right, of course from the function, from x to the 4th plus 1 over negative x squared minus 1, x to the 4th plus 1, negative x squared, x plus 1, x minus 1. I need the answer. And the same with the other 2. I need limit as x approaches 1 from the left, from x to the 4th plus 1, negative x squared minus 1. And limit, I should have used plus or minus. I mean this. It doesn't matter. 1 from the right, x to the 4th. I don't want you to get the impression that I'm changing anything on you, so I'm gonna change that. X plus 1. It's the same function. And of course, for the last one, negative 1. So limit x approaches negative 1 from the left, from x to the 4th plus 1, negative x squared, x plus 1, x minus 1, and limit as x approaches negative 1 from the right, x to the 4th plus 1, negative x squared, x plus 1, x minus 1. Of course, these are separate. They're not this, right? So I'm going to have to find a number for each. Basically, infinity, the sign of the infinity. Okay, so with 0 from the left, of course they are all a number over 0. There is no other way. They are vertical asymptotes. So all these must be infinity or negative infinity. So 0 from the left, it doesn't matter. The top is still positive for all of them. No matter what I do, I shouldn't even worry about the top. The top is always positive. Nobody cares about it. But the denominator will give us the sign. This will not give us the sign. Do not worry about it. Don't even look at it. It can be there or not. It's not going to make any difference. So 0 from the left, imagine negative 0.1. Negative 0.1 plus 1, this is positive. Negative 0.1 minus 1, this is negative, but there is a minus in front. So I see two negatives. The positives don't count, so this must be infinity. 0 from the right, 0.1. 0.1, positive. 0.1, negative. And negative in front. So this is again positive infinity. 1 from the left, 0.9. 0.9 minus 1, negative. 0.9 plus 1, positive. Two negatives, positive, infinity. 1 from the right, positive, positive, negative, negative, infinity. Negative 1 from the left, negative 1.1. Negative 1.1, negative 1.1, three negatives. Negative infinity, and negative 1 on the right, negative 0.9. Negative 0.9, positive, negative, negative, positive, infinity. So it's not sufficient to simply say this function has a vertical asymptote at 0, 1, or negative 1. You have to determine the limits left and right. And you will see in the next chapter, actually in chapter 4, you'll see what happens. And we need all these limits. So for now, I could say I accomplished this. And of course this. There are no holes in the graph. There are three vertical asymptotes, and I also determined their limits, left and right. Now the final step is to find the limit at positive and negative infinity. So when I find the limit positive and negative infinity, I prefer the unfactored form. So I have limit of x to the fourth plus 1 divided by negative x to the fourth plus x squared as x approaches infinity. And like before, I'm going to ask you what is the degree at the top, and you will say 4. And then, of course, we will factor out. So, of course, this is infinity over infinity. It's an indeterminate case. We have no idea what we come up with. Yes, we do if we remember from pre-calc what this is. So you said x to the fourth. And then I'm going to ask you the same question about the denominator. What will you say the denominator, what is the degree of the denominator? 4. So we're going to factor out x to the fourth, even if x to the fourth is not a common factor. And what do I do next? What is left inside? Excellent. 1 plus 1 over x to the fourth. Great job. What is left inside here? Yes? Plus 1 over. Very good. Awesome. Great job. Thank you. Both of you. Thank you. Now, of course, this will go away. And now I ask myself, where does this go? Remember, only when x approaches infinity. Because if x approaches 2, this is 1 over 16. But when x approaches infinity, it's a different story. What does it equal to? Excellent. What does this? Where does this go?
0.
Awesome. What is the final answer? Indeed. Which means y equals negative 1 is horizontal asymptote at both. We did not use the fact that x approached infinity or negative infinity. Doesn't make any difference. A rational function cannot, if it's a pure rational function, not radicals over whatever, pure rational function cannot have more than one horizontal asymptote. So this is at plus and minus infinity. Again, this is another problem that was quite long. Why was it so long? It was long because we had to determine the limits left and right, and it had 3 vertical asymptotes. But when it comes to horizontal asymptote, it was not that bad. Questions for me, please? Questions? Okay, so I would like now us to choose a problem in which we're asked to find an example of a function that fulfills the given conditions. You choose. Let's go with 9. Very good. So allow me a second to copy all the information so I can put the book aside. I don't need it. Okay, so we're looking at problem 9 on page 140. And we have f of 0 is 3. And we have limit of f of x as x approaches, limit of f of x as x approaches 0 from the left. They say that is 4. And we have limit as x approaches 0 from the right of f of x. They say it's 2. I think that's what it says, yes. Then limit as x approaches negative infinity from f of x, they say equals negative infinity. And then limit of f of x as x approaches 4 from the left. Yes, negative infinity. Limit as of f of x as x approaches 4 from the right is positive infinity. And one more, limit of f of x is 3 when x approaches infinity. Another problem that seems to be long, but I think it's going to be very clear in a moment. Please always summarize the information before you start, before you work on any of this. Summarize the information. So I'm going to put everything I see here in this table. Here's how I start. I start with f of 0. Done. I continue with limit of f of x as x approaches infinity, 3. Okay. Done. Then I see limit of f of x as x approaches negative infinity, negative infinity. Done. Then I see the limit of f of x as x approaches 0 from the right, 2. Limit of f of x as x approaches 0 from the left, 4. Finally, something happens at 4. Okay. The limit on the left-hand side of 4, negative infinity. Done. The limit on the right-hand side of 4, positive infinity. Done. I may put something that I want in here or not. It doesn't matter. You can make up a point if you want to. We're only told to present an example of a function, of a graph of a function that complies with all the given conditions, but it's up to you if you want to add stuff to it. That's up to you. As long as the function complies with the given conditions and the extra, it's up to you. So now, I'm going to say, that's my choice, that x equals 4. At x equals 4, the function is undefined, so it's a vertical asymptote. Obviously, I'm going to say, and this is clear, that y equals 3 is a horizontal asymptote at infinity only, because this is not 3. These are my choices. And accordingly, I'm going to graph I will present first the vertical asymptote at 4. That's my choice. Then I will present the horizontal asymptote at 3. And since I have to present the whole function, the whole line, I cannot just copy a piece. And now I start the graph. These are all not part of the graph. So the graph is 0, 3. On the left-hand side of 0 is 4. On the right-hand side of 0 is 2. I'm going to come up with this piece that I like this way. Then I'm going to come up with this piece that I like this way. Zero, 3. Okay, and now the final step is on this side. And here's my graph. Can you come up with something else? Yes, you can do this if you want. You can do this if you want. It doesn't matter. But all conditions are fulfilled. The function is coming from -infinity and approaching 4. At 0, the function is 3. On this side, at 0, on the right-hand side is 2, and it goes to -infinity. I decided to have a vertical asymptote here. And then on the right-hand side of 4, it comes from positive infinity and goes to a horizontal asymptote at 3. So without, I would have not, but that's me, I would have not been able to simply look at this and come up with this graph without summarizing the information from left to right, which is now much easier to see what I have to do. We are going to use the same table throughout the semester when we graph functions. Any questions here? Any questions for me? Now, the last 2 sections deal with what we've been dealing with the entire chapter. But this time, we are talking about a concept that we are putting together 2 pieces that we've discussed. Okay. So finally, 2.7 and 2.8 together. I don't want to put the title in. We're going to put the title in a minute after we discuss a few things here. Let's go back to something we discussed a long time ago at the very beginning of the semester, 3 weeks ago, I should say. And you will recognize this. Of course, you will recognize this. Of course, you will recognize this. If this is x, please tell me what this is. Not yet. This is here. The x plus h is here. Very good, of course. F of x, and of course f of x plus h. Nothing new. Then we drew the secant line. We determined the slope of the secant line. Can anyone tell us what the slope of the secant line equals to? Very good. F of x plus h minus f of x divided by x plus h minus x, but that would be h, which we know what it means. What does it mean? Very good. It is the difference quotient. Perfect so far. And then we said that if Q gets closer to P, the slope of the secant line PQ approaches. Nothing new so far. I'm just refreshing your memory on what we've done so far. So if Q gets closer and closer to P, which means if you want H approaches 0, the slope of the secant line PQ, the slope of the secant line PQ will get closer and closer to the slope of the tangent line at P. But now we have a mechanism. We don't no longer write this. We don't like to write this because we have an operator that we discussed for 2 weeks almost. What is that operator that I'm talking about? Very good, awesome. The limit operator as h approaches 0 from f of x plus h minus f of x divided by h. What will this represent? This time, because I put the limit, I can write the equal symbol. Here I could not write the equal symbol. Here I could only say that when h approaches 0, the slope of the secant line approaches the slope of the tangent line at P. But now I can write the equal symbol, and what will that equal to? Indeed, the slope of the tangent line at P. This has a name. So one more time. When we put together the difference quotient with the limit operator, this has a name. Anyone remembers or knows the name of this? Exactly. This is f prime of x, and it's the derivative of f of x. Now we have to talk and we have to write down what it means and what it gives us. But let's go back for a moment. So when we combine two concepts that we've been working on in chapter 2, the concept of the rate of change, which is the difference quotient, and we put that together with the concept of a limit. Putting these two concepts together gives us the derivative of the function, which is a function, another function, not the function itself. It could be. There is one function that has this, its derivative, the same thing. So what does this mean? Do you remember what we said this was? Yeah, the slope of the tangent line, which gives the instantaneous rate of change. I'm going to put this in writing for you. This represents the instantaneous rate of change of a function at any point under certain conditions. So what else can it be? The instantaneous velocity, if the function is the distance, and the derivative is the same thing. It gives us the slope of the tangent line at P at any point under certain conditions. And it's also the instantaneous velocity if the function is a distance function. In short, the derivative of f of x. It gives us the rate of change of this function at any point, comma, under certain conditions. The conditions are conditions of differentiability, and we're going to talk about the differentiability right now. But first, let's write what this means, and then we'll write the conditions. So, f prime of x, it's the derivative function of f of x. Also, it gives the rate of change at any point where the derivative exists. We say, instead of saying that, where f of x is differentiable. It gives a rate of change at any point where f of x is differentiable. In which conditions or situations a function is not differentiable? It does not have a derivative, in other words. a function is not differentiable one, if it is not continuous. So here is an example. At point A, the function is not differentiable. Of course, if it's a removable discontinuity, it's a different story. But if it's an infinite, so whenever it's not continuous, including, of course, the removable, if the function is not continuous, the function is not differentiable at that point. So here's a relationship that we have to understand. Continuity, differentiability. Is this correct? Does this imply that? Is this correct, or they're both correct? Before you answer, let me give you 3 examples. Don't answer just yet. I'll come back. And number 2. 1, when the function is not continuous, the function is not differentiable. Cusp. 3. Corner. I'll give examples from both. 4. Vertical tangent. What do you mean by cusp? Here's a function with a cusp. At this point, the function is not differentiable. It doesn't have a tangent, does not have a unique tangent. Here's the tangent on this side, and here's the tangent on this side. The function does not have a unique tangent. If it doesn't have a unique tangent, the function is not differentiable at that point. Corner. Very good, awesome. So here is an absolute value situation. And this is a corner. Again, at this point, there are 2 tangents. Not one, not unique tangent. And here's another situation of vertical tangent. This graph has a vertical tangent. So, a function is not differentiable if it is not continuous. It's not differentiable at the point if it has a cusp. It's not differentiable at the point if it has a corner. And it's not differentiable at this point when it has a vertical tangent. So coming back now, and we can answer this connection. Notice that this function is continuous everywhere. Notice that this function is continuous everywhere. And this function is continuous everywhere. So, finally, continuity implies differentiability, yes or no? The answer is no. No. The function is continuous, but it's not differentiable. The function is continuous, but not differentiable. And the function is continuous, but not differentiable. Now, if the function is differentiable, does that guarantee continuity?
Yes.
Correct. If a function is differentiable, if I tell you that a function is differentiable everywhere, you know it must be continuous everywhere.